Okay, welcome back, students. Let's begin lecture for today. Let me bring this down a little bit. Get your clicker ready to click. We're going to have a calculation at the end of class today, the thermal equilibrium temperature calculation. And your homework, the last item on homework 16, is the very first baby step in a thermal equilibrium temperature calculation. So we're going to work it all the way through to the final equilibrium temperature today. But I'm going to give you some instruction on why we do it and how we do it using heat transport concepts. And just to let you know, when we began the semester with basic dynamics, like here's a picture of some guy at the Orlando Eye doing the right-hand rule, angular momentum, angular velocity, and so forth. But what we've been doing the past week or two has been a transition to something extremely complex. Now, this is a very famous photograph from the Sierra Nevada mountains out in California. It's just a thunderstorm coming up. But if you look at this photo is a story of water and rock, really. I mean, there's liquid water in this lake. There's crystalline water in the snow. There's water vapor in the air that you can't see, and these clouds are micro droplets of liquid water, and eventually they're going to form, they're going to form big raindrops and fall. If you look at it, it's possible that some of it's going to fall as snow because there's already snow up on that mountain. And boy, just looking at this picture, it makes me homesick for out west where I used to live. So if you ever get out that way, just try if you ever get out to Colorado or Montana, New Mexico, try to get up in the mountains. It'll really open your eyes. So let's talk about why we actually make this transition. We're studying complex systems. For instance, the aurora borealis. Here's another very complex atmospheric system. It's not really involved too much with water molecules, but stuff up in the upper atmosphere that we see as the aurora borealis. I've seen, oh my goodness, one night out in Montana, I was coming from a friend's house who had a cabin way up in the mountain, and I was walking out to my vehicle, my truck, out this, dirt road to where I parked it, and I looked up and I saw the entire sky from west to east and from north to south. It looked like it was on fire. It was undulating orange and green and red and blue and stuff, and I thought, oh my God, the Russians have nuked us. I thought it was the end of the world for about 2 seconds, and then when I recovered my mental equilibrium, I realized, oh no, this is the Northern Lights. And it was really cool. It was spectacular. And this is what it looks like from space. The reason that we can do, and the reason that we try to figure out these systems is we have this conviction or this set of assumptions about matter that, first of all, for instance, a gas is considered a collection of molecules, or, like helium is single atoms, oxygen is diatomic molecules, nitrogen is diatomic molecules, neon is monatomic. But anyways, we consider gas a collection of molecules, and we say to ourselves, all right, we've got zillions, a huge number 10 to the 23rd power or more individual particles, and they're far apart from each other in a gas. Now, in a liquid, they're close enough that they can interact and have a binding interaction. And in a crystal, in a solid, they're close enough to have a strong, rigid binding interaction. But for a gas, they're really far apart. And it has the way that we model a gas, and it seems to be righteous, is that they have a random distribution of speeds. Okay, so you can, and it's not totally, we found that it's not totally random, but there's a lot of randomness to it, and that they ricochet like BBs off of each other. They're not BBs, and if you looked at it, this is kind of an idealized view of a gas. If you were actually able to follow individual molecules, which we are not able to do, they would interact a little bit differently than BBs. But the BB approximation, or the billiard ball approximation, is fairly good. Okay, so they ricochet off of each other. Otherwise, we don't think of them as having gravitational interaction, for instance. So we don't worry about that. And the BB bouncing interaction is actually electromagnetic. It's electromagnetic repulsion. And they're so fast that they don't bind together. They just repel. They get the nuclei get close enough that they repel each other. And that's it. There's no other interaction. So no gravitational. We don't. It's there, but it's extremely weak. The strength of the gravitational interaction is really, 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 really small. Many powers of 10 smaller. It's like 10 to the 39th power smaller. Or so 1 over 10 to the 39th power. Or 1 over 10 to the 40th power. It's just extremely small, depending on how you calculate it. And the other thing that we're convinced, or that we convince ourselves must hold, is that Sir Isaac Newton was right, and that F equals ma, etc., apply for these little shrimpy molecules that we cannot see. And we can't see them. And recently we've been able to see a few of them in the lab, but in a gas, no way. Because they're just zipping around too fast. Eventually maybe we'll get some way to do it, using lasers or something. But, excuse me. But it's doubtful that we'll get that anytime soon, to see molecules, individual molecules in a gas. So what we do is we build up this model, high number, large number, no interaction other than ricochet, no gravitational interaction, random distribution of speeds, and then F equals ma, and then we put all that together. We use a lot of stats, a lot of trig, a lot of calculus, and we figure out from that if you think in terms of the kinetic energies of the molecules, there's zillions of different kinetic energies, zillions of different momenta, but there's only one average. You take any collection of anything, donuts, they're going to have an average radius, an average mass. There's only one, central measure. The average, there's only one. You just add them up and divide by how many. And same thing with these. And what we find is that, and this is something that I've mentioned earlier, that the average kinetic energy, we think of this is called the kinetic theory of a gas. And we think that if the kinetic theory, part 2 here of the outline, if all of that is righteous, then the average kinetic energy of the entire collection, which we know by applying stats and calculus and trig at the wazoo, it's going to be proportional to the temperature, and we found that that is true. And so the temperature of for instance, the temperature of the aurora borealis, I'm sure there are guys that know how to estimate that. And the temperature in this, think about this, all the different temperatures in the different collections of H2O molecules. The lake, that's liquid, right? So it's not below 273 Kelvin. The snow, that's solid, but it's not everywhere. So every snowdrift and glacier that you see up there, all right, all the or almost all the H2O is below 273. And then those clouds, they're up at altitude. Okay, so you got to think about, what's the temperature up at that altitude where you form water droplets? And what's the temperature of the water vapor that's rising to form those clouds? As it goes from the ground upward. So, this is our conviction about, the temperature and the average kinetic energy. Now, what I want to point out to you is a few other things, and this is actually going to lead us back to Dr. Max Planck. The distribution of energies and speeds in a gas forms a curve. All right, now the curve looks like this. All right, this is one example. This is called the Maxwell Boltzmann distribution, and it basically, the vertical scale, you can make a sketch of this. It's a bump that dips down on the left and it dips down on the right, but over here on the left is the slower molecules, and over here on the right, get my cursor over here on the right are the faster molecules. Now, the thing about this is, and we've measured this, we know that this is accurate. It's a theoretical curve that we've been able to verify fairly well. There's an average up here in the middle. The average is actually a little bit away from the peak. And also notice that it's a little bit steeper coming up from low speed, and it dips back down to zero for higher speeds, but not quite as steeply. So this is not a symmetrical, it's almost symmetrical. It's not, for instance, it's not a bell-shaped curve, if you've ever heard of that in a psych class or a stats class or something like this. It's not a bell-shaped curve. And you can relate it to the bell-shaped curve, the Gaussian curve and stuff, but this is a little bit different. All right, so now, this particular distribution, the most probable speed is here at the peak. That's, so the more particles that you have, so this is like a count of nitrogen molecules in a gas. And you have a lot of them at this, kind of a medium speed. And you have a fair number of slow ones, and you have a fair number of fast ones, but most of them are going to be up in this speed zone up here, all right, by this peak. And the average is just a little bit to the right of that, because the curve, you have fewer over here than you have in this slower regime over here than you have over here, because this one dips off a little bit more slowly. You've got a few more fast. If you're 10 meters per second faster than the peak, you've got a few more of those than you have 10 meters per second slower than the peak. So it's not symmetric. But anyways, the averages are like that. Now, the thing about it is, it's all temperature dependent. The shape of this distribution is temperature dependent. Now, here, what does that mean? Here's the way that two curves look. This is calculated very carefully. Draw the graph. Okay, vertical scale is proportional to the number of particles in the gas. And this one was also speeds. The previous one, this one over here, this one was also speeds. All right, this one's speeds. And then this one is also speeds. Okay? But here's the thing. 2,000 Kelvin is this red curve. So if you have a hot gas, 2,000 Kelvin, that's pretty hot. All right? That, that's hotter than a bakery, hotter than a foundry, 2,000. All right? And it has a peak over here. It's got a wider spread. It's not as sharp. Now the blue curve over here is 273, so that's absolute zero. So that's a gas at the temperature of 0 Celsius. All right. Now we're talking about a gas here, okay, and this is for helium. All right, for the helium gas molecule. So these are actually atoms. All right, and now and here's. All this stuff is temperature dependent, all right? The shape of each curve, all right? And the temperature dependence is down here. So the vertical scale is F a function of U, and here's the formula for it. Now don't worry about this formula other than to eyeball it and say to yourself, yuck, Dr. B. It's got logarithms in it, exponentials. Dr. B, that is NASTY. And you know what? I agree, it is kind of nasty looking. All right. But that's how you can see, look, here's e to the, and then in the denominator of the to the is temperature. But you also got temperature down here, capital T, in the denominator of this stuff out in front. But hey, wait a minute now. The stuff out in front, it's not just a quotient. It's a quotient to the 3/2 power. So that's the square root of the third power. Oh my goodness. Now don't worry about calculating. I wouldn't even want to calculate this. And I could do it if I needed to. All right, but I wouldn't, and you guys are not going to have to calculate that. But what I do want you to remember is that the distribution of energies is temperature dependent, and it shows up it shows up mathematically in this big fancy formula over here to the lower right. But for us, what I want you to think about is the shape. It changes the horizontal position of the peak, left or right. The higher the temperature, the further to the right. Out there with the big speeds. And it also controls the height, how sharp it is. So if you have something cold, you don't have a big spread in the energy, so your peak is fairly narrow. But if you have something hot, like this previous, let's get it back here. Okay, so the cold one here is the blue curve, and that one is kind of narrow. The hot one is the red one, and it's a little bit smushed out. There's a lot more mixing and stuff, okay, for something that's hot. So just remember that the shape of the curve, this distribution, is temperature dependent. And therefore, the location of the average of the speeds, and you can do something similar with the kinetic energies. You can do the 1/2 mv squared graph. That's no problem. This is just speeds. The square of this graph, it would look similar to this. And so the temperature dependence, it tells you where the average is going to be and where the peak is. And so all that stuff is temperature dependent. All right? And so that's so dim this out in your mind, this big fancy formula. Don't even write it down. And I'm now going to try to hypnotize you and tell you, all right, forget about this function. It's getting dimmer and dimmer in your mind. Give me $20 at the end of class. No, you don't have to do that. But anyways, do dim this out of your mind. Okay? It's really weird. Whoa, what is this? I don't want any of that. Grades? Hold on. I forgot to delete. This is like from the first day of classes. How did that get in there? Okay, now, Here's a question that I want to pose, a rhetorical question to you. How does Max Planck fit into this discussion? And his famous constant, H, that we've talked about a few times. Well, he fits into the discussion in terms of color. And remember, we talked about stuff that's red hot versus stuff that's, so hot it doesn't have any visible colors. It's mostly ultraviolet. Or something that's not even hot enough to get a lot of red. It's mostly infrared. So that color and temperature thing is what Max Planck was actually working on. So let's get into some of his details now. In the 1890s, he was studying thermal physics in detail, including the strength and he was looking at not just how many photons of light were coming from an object, but their wavelength, the entire spectrum of electromagnetic. And he was working out a theory of this idealized object called a black body. Now, the black body is an object, ideally, that is a perfect absorber of radiation. So the only way that you know that something has a color is like, so this young lad over here on the aisle on the left side of class has a bright green shirt, and it says fire on it. Okay, that's right. Okay, stand up and take a bow. Go ahead, stand up and take a bow. Yep. Dude, you dropped your notebook. Anyway, so the only way that you know that he has a green shirt is because the light, if we turn out all the light, you ever hear that saying, all cats are gray at night? That's because there's not enough light to actually see what color the cat is. And if we turn out all the lights, what is your first name? Nate. Nate, you wouldn't know if he has green, red, or blue, or what, or a white T-shirt or black. You wouldn't even see it. All right. So the only reason that you know it is because it's reflecting. So a perfect absorber of radiation won't have a color. It'll be black. All right. But by the same token, it is also a perfect emitter. Now that doesn't mean it's a reflector. That means it's an emitter. And that's like saying that you take something, you put it in the fire, and you heat it up until it's red hot, or whatever the color is. Now, what they were looking at in Max Planck's day were distribution of intensity of light. And guess what distribution it had? Dun, 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 dun. Looked just like the Maxwell Boltzmann distribution. Except that there were some cool features to it. The temperature dependence, let me get my cursor over here. The temperature dependence, here's 5,500 Kelvin. That's close to the temperature of the SUN. Here's 5,000, 4,500, 4,000, and 3,500. These are 5 different spectra. And the vertical scale here is the energy of the light coming at each of these wavelengths down here. And so here's it's still pretty hot, 3,500 Kelvin, and it's putting out a lot of light at this band up here. Now the horizontal scale is the wavelength of the light, and we'll be getting into waves and stuff next week, maybe this week. And so this, for instance, 3,500, it's down here at about 800 Kelvin, 800 nanometers, right? 4,000. And you can notice that the peaks move a little bit to the left. Now, in Max Planck's day, they could measure this. And I've done this in the lab myself. You heat it up to a certain temperature, and then you put it through a prism or some other dispersion device. And then you measure the intensity of the reds. You measure the intensity of the oranges. You measure the intensity of the yellows, greens, blues, indigo, violet. You measure the intensity of the ultraviolet. You go back and measure the intensity of the infrared. And then you plot them up, you plot the intensities, and it works out like this for each temperature. Okay, now here's a band. See if you can sketch that in on your notes. The visible band of light, so from red to violet, is from 400 to about 700 nanometers. And 400 nanometers is considered violet. And 700 nanometers is considered red, the last of the reds that we can see. So on this scale, the infrared is to the right and the ultraviolet's to the left of this kind of greenish block that I just highlighted for you. Now those look just like Maxwell Boltzmann distributions, all right? But nobody could figure out, in terms of wavelength, why it was coming out this way until Max Planck figured it out. And just as a side note, these temperatures, 3,500 up to 5,500, yeah, those are all there's many stars that we see. When we look at a star and we see that it's peaking in the over here at this color, we think, okay, that's about, that's about 600 nanometers or so. That's going to be kind of a greenish star. And our star is actually a little bit hotter than that. And it's considered a yellowy green star. Okay? But even hotter than that, if you had something that was 7,500 Kelvin at the surface, its peak would be much taller, and it would be further to the left in the ultraviolet. And we see plenty of stars like that. So last week I mentioned the star Betelgeuse. Betelgeuse might be down there in about 3,500 or so. He's pretty red. Okay, 4,000. I should look up the temperature, surface temperature of Betelgeuse. Anyways, so here's where Max Planck came in. Nobody could figure out those spectra. They could measure that it peaked and that the peaks shifted left for higher temperatures, and they were taller. And then they dimmed out to the right. Everybody dimmed out to the right and dimmed out to the left. But nobody could figure out, well, why is wavelength and temperature, why are they related? They knew how, from the kinetic theory, that the kinetic energy and the temperature, but nobody figured out why the wavelength of light, so they were thinking, well, okay, I've got a metal object, and usually you use metal or ceramic for your your approximate black body. And what I did when I was doing this in the lab, we just had a box that we lined with ceramic tiles, and embedded in all the tiles were little coils of wire that we could pump a lot of energy into, just like your stove at home. If you have an electric stove, you turn on the electricity and they get so hot, turn it up to high, it gets red hot. Okay, and you heat up your food and, boil water and stuff like that. So, people had measured that, and what he did was he said, look, if we think of all the little atoms in those ceramic tiles or metal, whatever it is that I'm using as my black body, I could figure out 1/2 mv squared and temperature, that's nice, but I have no idea how to get a wavelength out of that. He said, look, if you make its energy proportional to h, some constant, and it has to be some multiple of h and a bunch of other constants like speed of light and stuff, he said, you can explain and put the peak wherever you want, temperature by temperature, and it will work. Some scientists had figured out, well, I've got the right-hand side of that, this set of, some guys had figured out the infrared side of this, but they couldn't get their theory couldn't get it to curve back down and dip down on the left on the ultraviolet side. And other guys had said, well, I can handle the ultraviolet side, but I can't get it to dip back down in the infrared end, on the right side of this diagram. But Max Planck, he figured it all out. He got it. So he introduced this quantum of energy and his constant H. It turns out that H times the frequency of the light is equal to the energy of the photon of light. And he was able to explain those spectra. And actually, and this is like in 1899 or so when he was doing this, that's when the quantum science revolution began. And it's now, 120 years ago or so when he was developing all this stuff. But at the time, and it's interesting, he was not a revolutionary, wild-eyed, crazy guy, some scientists like to cultivate this persona that, I'm a rebel and, I'm wild and crazy and everything, and I don't believe, but it's a bunch of BS most of the time. But this guy was look at him, he looks like a banker, a banker from 1910. But yet, he came up with this amazing theory, and it works, and it still works. Planck's constant, the one constant to rule them all. And this is the guy that developed it. Now, we're not done talking about Planck's constant. This is like F equals ma. We're going to keep talking about F equals ma, and from this day forward, we're going to keep talking about Planck's constant most of the time. Now, here's a few other everyday temperatures and where they peak. Now, room temperature, it's about 290 Kelvin, and that's infrared. Human body, a little bit hotter, infrared. Now, why is that important? Well, if you have night vision goggles, you're out in some desert, in Iraq or something, and in the desert it gets cold at night, but us humans are easy to spot because we're always 98.6 plus or minus a degree or so. And so you can make it out in infrared. You can't see it visibly at night, but against the cold background of the desert, oh yeah, you got it. And the cold background of space, yeah, we got it. We can see stuff up there in orbit in infrared that we can see a lot of stuff up there. Standard temperature and pressure. So this is like the chemistry class in chemistry lab, 273 Kelvin. That's the freezing point of water. The reason they use that is because it's easy to replicate that temperature with ice water, a water bath. Mount Everest, a little bit colder, 238 Kelvin. Peak temperature, dittos, infrared. Even up there on Mount Everest. All right. But the surface of the SUN, about 5,800 Kelvin, and oh my goodness. Peak colors, actually, the most energy comes through in the green wavelengths. And I always thought that was kind of interesting. Because if you think about it, what color are plants? Almost all plant life on Earth has got a lot of green in it, right? For photosynthesis. That's what they say, right? But here's what, so you think, okay, a lot of energy from the sun, it's in green. Good, nice. But it's deceptive because, or it's complex because the only reason that you know that a plant is green is because it's reflecting, it's not using it. It's getting most of the energy of the sun in the green, but it's reflecting it back to you. It's probably reflecting some blue, some red, orange, and all that stuff from the sun. But most of what it reflects back to you is green. So it's not using it. It's just bing, back at you. So why is that? Why, and I'm sure some biologist has figured out, in the scheme of evolution, the evolutionary advantage of rejecting the most abundant color in sunlight. I'd like to find that out myself. I've never heard of why that's an evolutionary advantage, but apparently it is. For plants, anyways. Here's another interesting thing. Chlorophyll, what? It has this special structure. It's got kind of a ring. And in the middle of chlorophyll, I think there's like a magnesium atom, if I recall correctly. And then there's this ring-shaped structure around the Does anybody know that from biology? That has had biology class? So chlorophyll's got this magnesium, and then there's a ring structure around the magnesium. And you know what it looks like? It looks exactly like another colored substance that we use. We're mammals, right? And we have red blood. And the iron is in a ring-shaped structure very similar to what the magnesium is in chlorophyll, in hemoglobin, the protein hemoglobin. So it's kind of cool. There's a lot of interesting things. Being a scientist, you learn a lot of stuff. All right, let's make some applications of kinetic theory. Let's use our clickers for a couple questions here. And hopefully, you guys will let me get the iClicker going here. Oh, it's already running. All right, here we go. Start a new session. By the way, right now, both sections are, before I do this question, are 49 questions so far for the semester. This will be the 50th. All right, so hopefully you get a go nitro. Here's your first question about ammonia. Ammonia has this observable property. Go ahead and vote. Read carefully. Hopefully you know the answer to this. In other words, this is going to be graded, but hopefully everybody gets it. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. Yeah, the observable property is that it's pretty pungent. So if you walk into the kitchen and your MOM is using ammonia, it's going to be pretty pungent. To clean the floor or strip the wax or something. I don't know what you do with it. People use it. I don't know. So here's the thing. Now let's apply the kinetic theory to ammonia molecules, right? The smell diffuses through a hot room faster than it will if the room is colder. So the temperature of the gas, you can measure it. How long does it take for if your nose is 10 feet away and somebody opens from the bottle of ammonia, somebody opens the bottle, if the room is 90 degrees, you'll smell it sooner than if the room is 40 degrees. All right? And that's because the temperature correlates to the average kinetic energy. Now, if you have a really sensitive nose, you might smell it a little bit sooner in either case, but on average, yeah, that's what you're going to find. and that's because of the temperature of the gas. It evaporates from the, you open the bottle and it starts to evaporate, right? And then it fills the room. Eventually it's gonna be zipping around in all directions, and eventually it'll fill the entire room with pungency. And eventually you'll see it. Okay? So there's zillions of molecules, and they're in random motion. It's a gas. But eventually, there's zillions of kinetic energy states. But of course, there's only one average value. And that average kinetic energy is proportional to the Kelvin temperature. All right. Now, this brings us to this idea of diffusion of smelly ammonia fumes. Brings us to the whole idea of heat transport. So let's talk about heat transport now. And we've talked a little bit about kinetic theory. And kinetic theory is how we make sense of a lot about heat transport. Now, here are the three main heat transport modes. So heat energy could go from point A to point B in one of these three different modes: conduction, convection, and radiation. Now, we're going to tackle all three of these in turn. And then we're going to be able to make a calculation. Hopefully we'll have time for it before we dismiss. Let's see, we dismiss at 10:20, so we're doing all right. So let's talk about conduction. Actually, let's go. This picture is a great photo. It's one of these guys at the... Has anybody ever seen this in real life? Raise your hand if you've ever seen... Has anybody in here ever done it? You've done it? Oh my goodness. I've never had a student say yes to that question. No, seriously, I want to learn. Now, what did you do?
Well, my cousin told me what to do and I just did it. So, he told me to put it I forget what I put in my mouth, but, I wasn't supposed to swallow it.
Right, don't swallow it.
Then we had the fire that we just had. We probably shouldn't have. I burned, the sides of my mouth. But,
Whoa, you burned it.
Pretty cool, though. Just don't do it unless you know what you're doing, because you could really hurt yourself.
Yeah, so your cousin, what was it, kerosene or something?
Yeah, it was kerosene.
And it left a nasty taste. I mean, say...
It was disgusting. It was probably the worst thing I've ever put in my mouth. But, it was really cool, though. I did it outside my house.
Dude.
I think I was,
16?
16. Yeah.
Is there anybody here that's 16 or younger? Every once in a while we have some really young students. Man, I don't know. Anyways, that's what so you put it in there, and you had to have something else like a lighter of some kind, right?
Yeah.
And you spurt it out, and the lighter's right next to it, and
Yeah, and you have to position it correctly, because if you do it at the wrong angle, you'll just put out the flame, and then you just put this kerosene in your mouth for no reason, and then you have that nasty taste in your mouth. So you have to do it from an angle specifically, so that it hits the right amount of flame, so the flame goes out.
Cool. Now, what we just discussed is the idea of conduction. Physical contact of hot with cold. Now, the part of kerosene that's flammable is the vapor. When it comes out of your mouth, you're trying to vaporize it. You're putting it into, you spurt it out, right? You go, pfft.
Yeah, you can't completely let the water in.
Yeah, you can't just let it drop out in a big blob, you gotta, yeah. And so that makes it into droplets, and they're going to provide a lot more vapor. Now, kerosene does not evaporate very much, but it does, and it's the vapor that you ignite. And you have to have a lighter to ignite that vapor. Now, the vapor coming out of her mouth is going to be the temperature, above the temperature of the liquid kerosene that she put in her mouth, and close to the room temperature or the outside temperature where you're standing. All right? But that's going to be colder. That temperature is going to be colder than the flame. The flame won't go unless you can get it up to a certain temperature. So heat flows, into the cooler object relatively easy if it's in contact. This is what we call thermal contact. All right? So it's, so you're blurting out some kerosene over here in front of you, and if your lighter or your little flame stick is out here 2 feet away, it's not in contact. You're just going to be putting, blurting that stuff all over the front yard. And you're going to kill maybe you'll kill some weeds in the front yard, but that's about it. But if you want a cool fireball, you got to bring that light stick in close to what you're blurting out of your mouth, just like this guy. All right? And you can see what he's got in his right hand. Look at that. Same with this picture over here. He's got 2 of them. Right? And this guy's got 1. So physical contact, heat flows into the cooler one and out of the hotter one. So that's the heat transport. All right? It raises the temperature of the cooler object and lowers the temperature of the hotter one. Okay? Now, it doesn't take much to get it lit off, So this guy's he's still got a pretty hot lighter over there in his right hand. All right? But theoretically, it cooled off as soon as it nuked off, or as soon as it flamed up that kerosene. All right? So the fire breather has to use a light, some kind of a torch to light up the kerosene. Because it can't be, think about it, you don't want it to be burning already inside your mouth. I mean, that would be nice if you were Iron Man or something like that. But, or who's that guy with the eyeballs? In X-Men? Cyclops, yeah, Cyclops. I wonder if Cyclops, he could probably do it with his eyes. That would be cool. If Cyclops was doing this, all he has to do is just beep, just peek, light it right up. That'd be cool. Okay, now the counterexample to this, call it, is a conductor. An insulator. In other words, something that doesn't conduct heat very well. All right, you know what a good insulator is? Air. Air will conduct heat, but it's not very good. Let me see. Let me look around the classroom. Here in Florida, when the temperature dips below 75, I see a lot of people putting on fleeces and coats and hats and stuff. Yeah. And when I lived in St. Thomas down in the Virgin Islands, it was amazing. This time of year when the weather starts cooling off down there, you get some cold fronts that come through, and everybody's wearing hats and boots and gloves, and it's like 75 degrees out. But for those guys, they're used to 80s, year round. But anyways, air, you break out your parka, you break out your fleece, you break out your gloves, your insulated gloves, or your sleeping bag. That sleeping bag is filled with goose down maybe, or polyester fiber fill. All that stuff, it's not the fabric, it's not the feathers, the down, it's the fact that the fiber in the down or the polyester or whatever is quilting you, it traps air. It's the air that prevents heat motating from you to the cold outside. All right? So that, you're not getting cold, you're losing heat if you don't wear something like that. And so air is a great example of an insulator. And certain metals, most of the time metals are good conductors of heat. And most metals are also good conductors of electricity, and there's a reason that that's true. But I have seen from my pyromania days on campouts and canoe trips and stuff, throwing stuff in the fire, you can put a piece of stainless steel in, some versions of stainless steel, you could put it in the campfire and get the tip of it red hot. The part that's in the campfire, you can get it red hot, but you can hold the far end of it that's out of with your bare hand, because stainless steel doesn't conduct heat very well. Versus regular steel, rebar, you got, we've done that. We used to do that too, find a piece of rebar somewhere out in the wilderness from loggers or something, and just put it in the campfire and you get it hot, but then you have to use a t-shirt rolled up and stuff so you don't burn your hands on the rebar. Okay, convection. Let's talk about this. Bulk motion. Now, this fireball going up into the air, that's bulk motion. The fireball is rising. You can see it. He's arched his back. He's aimed his blurp, kind of upward and stuff. And convection happens if conduction is not really efficient. And this guy's blurping out into air. And air will conduct heat, but not really efficiently. So what happens, this fireball stays hot. It is radiating away, and if you were near it, you would feel the heat, but not enough to convert it from a hot, boiling gas. And since stuff that's hot is usually less dense, that's why water vapor rises. It gets hot during the day when the sun warms it up, and then it rises up to a certain altitude by the afternoon, and then it starts to rain. It forms thunderstorms. So if it's hotter, it's usually less dense. So you have this blob of hot stuff that's less dense than the surrounding air, like this guy. Up she goes. You got buoyancy. You have something of low density immersed in a substance of higher density. Now, the air is not very dense, but the flame is way hotter than the air. And even though it's kerosene, that's a fairly heavy molecule, it's still hot enough to be buoyant enough because it rises. You can see it. All right? And that's buoyancy. So the fireball is going to go upward as a result of that. And it's going to keep going upward until it does radiate away and conduct away enough. Eventually the air will, conduct heat away from it, and the fireball will kind of disappear. All right, eventually. All right, but for the first moments. Now here's another example: the mantle of the earth. If you think about the mantle of the earth, it's a lot of molten lava and stuff down there, and eventually it's so high pressure. The further down you go, it's not even molten lava. It's just it's solid, but it's extremely hot. And so the mantle of the earth, it doesn't have really good conductivity in all places. So what happens sometimes is you get convection through the mantle of the earth up to the surface. And that's what Yellowstone National Park is. It's a super volcano. It's way out of the Pacific Rim. The Pacific Rim has volcanoes, the Ring of Fire they call it, all around the Pacific, from Alaska all the way down to Indonesia, in both directions. And, tons of volcanoes and stuff. But Yellowstone's out in the middle of the North Atlantic continent. Here's another example. Hawaii. Big volcanoes in Hawaii, but it's not on the rim of the Pacific. It's out there in the middle. So what happens is, for whatever reason, a plume of heat rises, and we got a plume of heat rising through North America. North America, the continental plate of North America is moving west over Yellowstone. And it's still, blazing up heat. Here's what it looks like. So scientists have figured out using seismology and studying the seismic waves that the stuff that's slower, where the seismic, they time it basically. It's kind of like stereo. They set a bunch of seismometers around Yellowstone, and they just listen to earthquakes, and they figure out, okay, by timing the pressure waves from the earthquakes, it's kind of like you triangulating, listening to something and saying, okay, the source is right over there. Instead of the source being over here to the right, etc. So they figure, so this is a picture. The red stuff here is the hot stuff, and it's blazing up. This is the bottom of this diagram here is 800 kilometers below the surface of the Earth. And Yellowstone is way up here, where it says capital Y. And here, these are two different views of it. Okay? And so what they do is they look at the speed of the sound waves, the pressure waves that from various earthquakes. Because there's all, I've seen the seismology graphs and stuff, from when I was living out in Montana. There's always little tiny earthquakes happening around Yellowstone. They're very small. But, we can measure them. If you're fairly close to Yellowstone, you can measure them on a good seismograph. And you analyze all that stuff, and you figure out that there's this plume of stuff here that has slower seismic waves and therefore is hotter. And so they've localized this plume of heat just blurbing up, and when it gets to the surface, it forms a big lake of burning molten lava, and when that gets too full, kablooey, you get a big, and that's what Yellowstone is. Yellowstone is what they call a super volcano, kind of like out in Hawaii, they got a really big volcanoes out there, really tall, but Yellowstone's even bigger, and it blew its top completely off. It completely shredded the upper part of the volcano, who knows, 10,000 years ago or whatever it was. And they think that we're due for another one soon. If that ever happens, say bye-bye to everybody out west, because all that volcanic ash is just going to cover everything. It's going to be a big disaster. Hopefully it won't happen very soon, but some people say, just like the San Andreas Fault, they say is overdue for the big one. And some people think, well, they think that Yellowstone might be due, but it might be, it's for Yellowstone, it's like plus or minus 1 million years or something like that. Whereas San Andreas, it's plus or minus a few years. I mean, they think it's going to happen soon. But anyway, so this is a mantle plume. So convection will occur. Here's another convection system that you've probably seen photos of. Hot air balloons. How does that work? Well, raise your hand if you've ever ridden in a hot air balloon. Anybody? One? You're not even raising your hand. Yeah, okay. Was it fun? Where was it? Here in Florida? Cool. Yeah. I've never actually been to one. They must be kind of. Was it fun? I bet. And there's a guy that's in charge of the hot air balloon, and he's got a big propane burner, right? And he recharges the hot air. He's got to, because it's gonna conduct away to the atmosphere and cool off, and therefore it's going to lose buoyancy. So he's got to recharge it with some more flame from that propane burner, and you can see it on the internet and stuff like that. But must have been really cool to actually do it. So our next chapter is going to be on waves and oscillations. So just so you know, that's where we're heading. But we still got a few things to do with heat transport, so let's continue. The third mode of transport is radiation, electromagnetic radiation. So this is photons of light, and the photons of light transport momentum and energy from point A to point B. So like the SUN, everything in our weather, in our oceans, is heated up by the SUN. The energy that we get from the sun. This huge source, huge amounts of energy. And it doesn't have to be visible light. It could be X-ray, ultraviolet. It could be infrared. Infrared's not going to heat things up very quickly, but it will. Microwave, You have a microwave oven. And you know what the microwave does is it zaps the water molecules in your food. It won't work for something that's completely dry without any water in it. So, or it won't work very well, I should say. So if the material absorbs the photons of light, in other words, if it doesn't reflect them like a mirror, then it's going to heat up. It's absorbing the momentum and energy and speaking of momentum, you can get momentum transfer from sunlight as well. And you may have heard this. This is not heat transport, but it's momentum transport. They're trying to develop something for spaceflight called a solar sail. And a wind sail here on Earth in a lake or out in the ocean it's a big piece of cloth and it catches the wind. And the wind transfers momentum through the sail to the mast and then to the boat itself. And the boat goes hopefully where you want it to go. And we're trying to develop, for the past 20 years, a workable solar sail because if you can get a solar sail that will catch photons from the sun to propel a spacecraft, you won't have to, you won't need any jet fuel, rocket fuel, you won't need any nuclear fuel, you just need maybe a little electricity, some solar cells to power your radios and stuff, to beam stuff back to Earth, but other than that, catch all those photons of light. The problem is, it works best in the inner solar system, and it kind of, gets a little bit shrimpier as you go further away, like out past Saturn and stuff. But, guys are working on it, seriously. NASA, I'm sure, and the Russians and stuff, the Chinese. Everybody's trying to do it. So anyway, so the substance absorbs some kinetic energy, some momentum, and they stops. And, the skin cells in your skin will stop ultraviolet from the sun, unless you got sunblock, and you get sunburn or skin cancer from that. So you got to be careful. And down here in the lower right, I've got a picture of astronauts on the moon, and yeah, those guys needed very, very fancy shielding. Because the amount of energy that the sun gets out this far, about 500 light seconds from the sun, is 1,370 joules per second per square meter. Now, 1,370 joules per second might not seem like a lot. That's 1,370 watts, okay? And that's for a square meter. So something about as big as this, a square about this wide. So like the front of this table here that has the document camera is maybe close to a square meter, maybe a little smaller. All right? And 1,370 watts is perfectly fine for running something like a microwave oven or a hair dryer. So you use stuff that if you had a square meter and you're outside the atmosphere of the Earth, up above all the clouds in the atmosphere, you can catch with a square meter of solar cells 1,370 watts. You run your hair dryer, run your microwave, run whatever you want that needs that many. If you need more than that, get a bigger solar cell, 2 square meters, or what have you. Now you may think, Dr. B, big deal, a hair dryer. If you calculate it, for instance, and I should do this for your homework assignment, homework 17, calculate the surface area of UCF, and then figure out how many joules per second. You could do that, length, the surface area of UCF is, basically length times width, right? So figure out how long and how wide UCF is, how big the footprint is. Multiply those two numbers together, that's how many square meters you got. And then multiply that by 1,370. And my wonderful students, in a second, for something the size of a city, the sun is putting enormous amount of energy. And we're talking about like the energy in an atomic bomb every second for something the size of a small city. And that's what hits the upper atmosphere above that city. And it's not an atomic bomb, but it's equivalent to the energy. I worked it out one time for the city of Ocala. I just looked up the surface area and worked it out. It's an enormous amount of energy. So we have to figure out ways to defeat that stuff. So up there on the moon, a lot of times spacecraft in orbit, they'll have this reflective substance, mylar, that will just, it's silver. It looks silver because it reflects everything, or almost everything. And it's very thin. And it's the stuff, and they invented it, I don't know, back in the 60s or the 50s. And they use it all over the space program to defeat solar heat gain. Right? Here's another thing that the astronauts use. They've got the best equipment, the astronauts. And some pilots in the Air Force and the Navy that have special planes, that fly at high altitudes and stuff, they'll have gold visors. They'll have it's plated with a thin layer of gold so you can see through it, but the gold will reflect most of the light that comes in. And that's to protect the eyes of the astronauts and because he's operating up there. There's no atmosphere on the moon. And if you look at it here in this picture, you can see those shadows are pretty long, so it's almost sundown on the moon in this picture. Right? So they have to be really careful about that. But on the other hand, there's other things we want to optimize. We want to get as much solar heat as possible. So that's like this thing, the solar hot water collector or solar heat collector for your hot water system. All right, so that one you don't want to block anything. You want to, make as much of it available as you can. So it just depends on what you're trying to do. If you're trying to survive in space, you got to manage your heat budget really carefully. And they do. They have good equipment. They've figured it all out. These guys, the SR-71 Blackbird, an amazing airplane. Amazing. And they're in mothballs now, but hopefully, maybe one of these days I'll have to bring them back out. Notice it's painted black. And there's a reason. There's a couple reasons for that. This machine, it goes. Nobody outside the government, most people inside the government don't know how the top speed of this baby. But everybody knows that it can run so fast through the atmosphere that the leading edge, the nose, the leading edge of the wing, will turn red hot. And I've seen them when I was out in Montana. I was stargazing one time, and I was looking for the meteor showers. And I saw this red V-shaped object go across from northwest to southeast. And I wasn't thinking about this SR-71 Blackbird. I was looking for, the meteor shower, the Perseid meteor shower. And I saw this, so I thought to myself, oh, it's a V-shaped, formation of geese heading south for the winter. And it's up so high that it's getting the first rays of the sun. That's how high they are up there. And so I thought, okay, well, that's nice. But then a couple hours later, I'm still out there looking at the meteor shower, and I see them coming back the other way, the same speed. They're heading back. And I thought, well, that can't be right. It must be that's when I thought, this is a UFO, And so I'm up there looking at, or I'm out in the middle of a soccer field. And, I'm laying down just watching the meteors come in, the meteor shower. And I see this thing, and then when you're out there, sometimes you nod off to sleep, and sometimes you wake up. And anyways, I was awake for both, on the way down and on the way back. And then eventually I went in and slept in, and then I went and I told and this is when I was in grad school. So I told my thesis advisor, I said, Doc, and this is before I was a doctor. I was working on being a doctor. I said, Doc, I saw a UFO last night. And he wore glasses, right? So he's wearing he always wears glasses. So he takes his glasses down like this. Son, like you didn't see no UFO. Because he's a scientist, right? He's an astrophysicist, just like me. And he said, son, and I was really embarrassed. But, I told my buddies, my classmates in grad school. And so one of them said, you know what that was? It wasn't a UFO. It was a UFO for about 6 hours. And then one of my buddies said, they just took the Blackbird out of retirement. And at the time, they were planning to deploy it somewhere over in the Middle East. And they were and he said, you saw the SR-71 Blackbird doing practice. And that's what they did. They're so high up and flying so fast. So they were flying from Alaska to Canada and back. That's what those guys do. And I was able to see it. So this is an amazing airplane. Now, last few minutes, I want to go through, and we're going to look at the kinetic theory again and think in terms of kinetic energy and how heat and this is going to be conduction. This is going to be a model of conduction. And two objects at different temperatures, what we say is they're not in thermal equilibrium. All right, so substance X and substance Y, or substance J and substance U on the homework, different temperatures. So if substance Y has a higher temperature, it'll go out, the kinetic energy will transport out of Y and into X. All right? And that's because the faster molecules, they get there faster. Now, molecules are, probably migrating over from X to Y, but they're not so fast. But from Y, they're zipping on average. They're zipping. All right, and that is why the heat. So here's a big red arrow of energy, kinetic energy. Go ahead and sketch that in. Big red arrow. From Y to X. Now, X is going to swap energies with Y, but it's going to be a lot pokier. So give it kind of a little arrow to signify, yeah, those molecules can motate over to substance Y, but they're kind of taking their time. It's like you heading for Chick-fil-A. Either you're running or over to Chick-fil-A, or you already got your stuff at Chick-fil-A and you're just walking to class now. You got it. All right, so that's what we got here. All right. Now, that means there's a net transfer of kinetic energy on average. And eventually the average kinetic energy, the substance Y's dipping, it's losing some of the fast molecules, and substance X is gaining them. Whatever Y loses, X gains. And so eventually the averages are going to start to get, so here's Y up here, high average, here's X down here, lower average, and eventually, and when they get to the same temperature, they're still going to be exchanging, but it'll be equal kinetic energy. So you won't have any net transfer. Okay? So then you have two arrows, same size in both directions. So that is what we call thermal equilibrium. Now, when we get to class on Thursday, oh my goodness. We haven't worked this out. So we'll work this out on Thursday, And unfortunately, that means no homework. Darn it, don't you hate that? All right, I'll see you guys on Thursday. No homework.